Hello, thank you for joining me. I will talk about an approach towards optimal separations between quantum and randomized query complexities. There are some exciting news at the end. I'm talking about the black box or query model. Think of a huge string X of length capital N that sits inside the black box. The only way that you can access this string is by asking what's the ith coordinate and getting 1 bit back. You want to ask as few queries as possible and say whether the string X or the black box satisfies some property or not. This is very common in query complexity and also in property testing. So the query complexity measures how many queries, possibly adaptive, we need to make to the black box in order to determine whether the property holds or not. A property can be described by a Boolean function, f, mapping all Boolean strings of length n into +1 or -1. A query algorithm can be described alternatively as a decision tree. This describes all possible computational paths in one picture. If the query algorithm makes d queries, then the decision tree would be of depth at most d, and it naturally describes a computation where you start at the root and follow the path described by the input until you reach a leaf and then output either 1 or -1. This was the deterministic model. What about the randomized model? Where in the randomized model, we allow also to flip coins, and we can also flip all the coins in advance in the beginning, and this just gives us a distribution over deterministic decision trees. So we flip some coins and we choose one of these n trees, T1 up to Tn, and then we are making at most d queries deterministically. We say that a randomized decision tree computes a function if it outputs the right value of the function with probability at least 2/3 on every input. And again, we'll denote by R of f the minimal depth for a randomized decision tree computing a function, or the randomized query complexity of a function f. The next thing we want to do is talk about the quantum analog of this model. Unfortunately, there's not a nice picture as a decision tree for the quantum case, so we need to go back to the black box picture. Everything in a quantum algorithm needs to be a unitary transformation. So in this case, the query itself is also a unitary transformation. It maps the standard basis I into xi multiplied by I. So notice that xi is either plus or -1. So this transformation preserves the norm of the standard basis, and it can be also naturally generalized to any superposition over the standard basis. A general T-query quantum algorithm applies a sequence of 2t+1 unitaries. You first apply U1 and then O of x, where O of x is this oracle query to x. Then you apply U2 and then O of x again, U3, O of x again, so on and so forth for t steps. And in the end, you apply another unitary ut+1. Finally, you measure the state and you get some string, and you decide to accept or reject based on the string that you got. A quantum query algorithm computes a function if it outputs the correct value with probability at least 2/3 for every input x. And this naturally defines the analog of the randomized decision tree into the quantum setting. So this brings us to the motivating question of this talk. We want to know whether quantum algorithms gives us an advantage over randomized or deterministic algorithms. Unfortunately, we don't know it in the Turing machine model, because this is even harder than the P versus P space question. However, we may ask this question in the more confined model of the black box setting or the query model. One example is Grover search. It offers a quadratic speedup over the query complexity of the OR function. Let's say that you want to say whether the input string is all -1s or at least one of the entries is a +1. Deterministically, this would require you querying all the bits. Using a randomized decision tree, you still need to query linear amount of bits in order to be correct with probability 2/3. However, using quantum queries, Grover showed how to do this in times square root n. So this gives us a quadratic speedup for quantum versus randomized. Bills, Buhrman, Cleve, Muska, and de Wolf show that speedups can be at most polynomial. Any total function that is defined for all possible strings of length n have their randomized query complexity at most the quantum query complexity raised to the power 6. So in this setting, where the function is defined on all inputs, we cannot have more than a 6-power saving. Surprisingly, Aaronson, Ben David, and Kothari showed that there are functions where the separation or the speedup is even greater than the OR function. They showed that Grover is not the optimal separation. They constructed a function based on the cheat sheet method, and they showed that the quantum speedup is to the power of 2.5, better than quadratic speedup. In a recent result, with Aaronson, Ben David, Kothari, and Rao, we show that this result of Bills and al. Can be tightened, and the randomized query complexity is most the quantum query complexity raised to the 4th power. So we know that the two complexities are somewhat between 4th power apart to 2.5 power apart. Okay, so far it seems that quantum gives us some speedups, but only polynomials. So what's the big deal? Well, if we change the game a bit and allow for partial functions or promise problems, then we get super polynomial and even exponential separations. So there are a lot of beautiful results in this slide, but the short summary of that is that we have exponential or even more separation. By even more, I mean that the quantum query complexity can be constant, whereas the randomized query complexity can be square root n. However, in this beautiful line of work, you can see that in the right-hand side, in the randomized query complexity, in all these exponential separations, the randomized complexity was at most square root n. The question is this a coincidence or not? Aaronson-Ambainis raised this question. And more broadly, Buhrman, Fortnow, Newman, and Rorrelation ask, can we get the optimal separation where the quantum query complexity is constant and the randomized query complexity is linear in n? You have to read the entire string to know whether the probability holds if you're using a randomized algorithm, but you can do it with constant many queries if you're using a quantum algorithm. This turns out to be false. Aaronson-Ambainis showed that any quantum query algorithm that makes t queries can be simulated by a randomized query algorithm that makes n to the 1 minus 1 over 2t queries. So if t is constant, the randomized query complexity is sublinear. After this result of Aaronson and Ambainis, they naturally conjecture that this is also a possible separation, that it is possible to get a separation where the quantum query complexity is t and the randomized query complexity is n to the 1 minus 1 over 2t. They even suggested a candidate problem. They call this problem the k-fold Forrelation, where k is 2 times t. They showed that the quantum query complexity is indeed t for this problem, and they conjectured that the randomized complexity of it is n to the 1 minus 1 over 2t. They were able to show that the randomized query complexity is at least square root n, but this is the best that they were able to show. So this remained open since their work, and this is the starting point for our work. So next I want to define this Forrelation problem, and then I'm going to talk about the k-fold Forrelation problem and the new problem that we suggest for which we are able to show the bound. The new problem would be very related to this. Twofold Forrelation is defined as a problem on two vectors, x and y. The problem is to distinguish between yes cases and no cases. In the yes case, the inner product between the vector x and h of y is rather big. It's at least 0.6 times n. H is the Hadamard matrix that I'm going to show you in just a bit. In the no case, this inner product of x and hy is at most 0.1 times n. You can see that there is a gap between the yes and no instances. So this is really a promise problem. If we're getting anything in the middle, we don't need to guarantee anything. Let's just spell out what is this x inner product hy. You can open it up, and it's just the sum over all i's, the sum over all j's, xi, hij, yj. And all this thing is divided by n. The important thing about this Hadamard matrix is that all the entries of this matrix are rather small. They are of magnitude 1 over square root n. So either plus 1 over square root n or minus 1 over square root n. Aaronson suggested the Forrelation problem in an earlier paper in 2009, and he came up with a quantum algorithm for it. The quantum algorithm for twofold correlation is rather simple. You start with the all zeros state, you apply the Hadamard transform, then you query y, apply Hadamard again, query x, apply Hadamard again, and then measure. If you keep track of the amplitudes of the quantum state, you would see that the amplitude of the all zeros state is this sum that we seen in the previous slide. When you measure, you get the all zeros vector with probability, which is this amplitude squared. So this naturally gives us an algorithm. Just perform this measurement. If you got the all zeros vector, declare that this is correlated. If not, declare that this is uncorrelated. This would give us a gap between the yes and no instances. Yes instances would be accepted with 36% probability, and no instances with probability 1%. If we want to insist on succeeding with probability 2/3, we can do some amplification by repeating this experiment a few times and taking majority. Next, we want to define k-fold correlation. It turns out that it's much more natural to define k-fold correlation starting from the solution rather than from the problem. Think of k vectors. How can you generalize the previous solution that had two vectors, x and y, into k vectors, x1 up to xk? The natural thing would be to query these k vectors one by one. When we write in matrix notation the amplitudes, this would be equal to this following product. We take the zero state, multiply by h, then by the oracle to xk, then by h, then by the oracle to xk minus 1, and so on and so forth, until we multiply by the oracle of x1 and then h again. The first amplitude would be equal to phi of x, which is this twisted sum. We're summing over I1, I2 up to ik, and we have this product of elements that depends on the input x and on entries of the matrix H. So now that we've seen the solution, let's define the problem. The problem of k-fold correlation is given k vectors, x1 up to xk. All of them are of length capital N. Decide whether this phi of x is at least 0.6 or whether phi of x is at most 0.1. Again, this is a promise problem. Unfortunately, our new results do not apply for this Forrelation problem. We rather need to make two changes in it. The first change is that we take M to be a random orthogonal n by n matrix rather than the Hadamard matrix. So we pick M uniformly at random from all possible orthogonal n by n matrices, and our statement holds with high probability over this choice. So now that we have this matrix M, we can define the Rorrelation problem with respect to the matrix M. We are given k vectors, and we need to decide whether these k vectors have phi of m of x greater than some value, here it's 2 to the minus k, or smaller than half times this value. Again, phi of m of x is the same thing that we've seen in the last slide, where I just replaced the Hadamard matrix with the matrix M. And similarly, the same algorithm that solves Forrelation can solve Rorrelation, where we just replace the Hadamard transform between every two queries with the matrix M. The second difference is the threshold that we chose for yes and no instances. This is for some technical reasons that I will not get into. What do we want from the matrix M? Recall the matrix M should be an orthogonal n by n matrix. We say that such a matrix is good if any L by L submatrix of it has spectral norm roughly square root L over n. And we want this to hold for all values of L between 1 and n. So let's see the two extreme cases. When L equals 1, we want all the entries of the matrix to be of magnitude roughly 1 over square root n. This holds for the Hadamard matrix. But we also want that when we increase the size of the submatrix, the spectral norm of the submatrix doesn't go to 1 so fast. Unfortunately, in the Hadamard matrix, when we pick L to be square root n, the spectral norm of this square root n by square root n submatrix could be 1. So a Hadamard matrix is not good. On the other hand, a random orthogonal matrix is good with high probability, and this will be used in the analysis. Our main result is as follows. We showed that if a matrix is any n by n orthogonal matrix, then there exists a quantum query algorithm that solves a k-fold Forrelation or Rorrelation with respect to M with at most 2 to the order k many queries. Here we think of k as some constant, so 2 to the order k is still a constant that doesn't depend on n. On the other hand, we show that if the matrix is good, then any randomized query complexity trying to solve this problem would require at least n to the 2/3 minus 1 over k queries. If we pick k to be a big enough constant depending on epsilon, then we'll get order 1 versus n to the 2/3 minus epsilon separation between quantum query complexity on one hand and randomized query complexity on the other. So this surpasses the square root n barrier that was noted by Aaronson-Ambainis. Furthermore, we pose a conjecture on the Fourier spectrum of standard decision trees, deterministic and randomized decision trees, and assuming this conjecture, the lower bound can be improved to n to the 1 minus 1 over k. I want to talk briefly about proof ideas and techniques. These two seminal results of Nisan, Szegedy on one hand and Bills, Buhrman, Cleve, Moskva, and de Wolf on the other shows a connection between randomized query complexity and low-degree polynomials on one hand and quantum query complexity and low-degree polynomials on the other. In both cases, the acceptance probability of a query algorithm making few queries can be captured by a low-degree polynomial. So it seems that low-degree polynomials don't capture the difference between the randomized and the quantum model. Both of them are captured by low-degree polynomials. The main idea from a previous paper with Ran Raz is that the sparsity of these polynomials, rather than their degree, can be quite different, and this could explain the difference between these two models. On one hand, shallow randomized decision trees have sparse polynomials. On the other hand, quantum query algorithms can have dense polynomials representing their acceptance probability. How do we measure sparsity? We use a slightly non-standard notion. We are looking at multilinear polynomials. These are polynomials where every variable appears to the power 0 or 1. So they can be represented as a sum over all subset of the coordinates between 1 and n, a coefficient for each subset, as, multiplied by a monomial, xs, which is just shortened to the product of xi, where I is in the set S. How do we capture sparsity? We first look only on the degree L terms. So think of it as some kind of refined version of sparsity where we only care about degree L coefficients of this multilinear polynomial. And we are counting not how many of them are non-zero, but rather the sum of absolute values of all these coefficients. So this is some relaxed notion of sparsity. Standard facts about Fourier spectrum of Boolean functions or bounded functions tells us that the sum of squares of these coefficients is at most 1. The sum of absolute values can be rather large, and it's largest when the coefficients are rather similar and spread around over all possible coefficients of degree L. If, on the other hand, they are concentrated on a few coefficients, then we get that the sum of absolute values is rather small. That's why we say that this captures sparsity, but note that this is not the traditional sense of sparsity. So let's see this in play. We saw this algorithm by Aaronson-Ambainis. Actually, the algorithms that we saw made K queries, but they gave a very clever argument how to reduce the number of queries to K over 2. And the acceptance probability of their algorithm is 1/2 times 1 plus phi of x. And recall that phi of x was this very nice sum. Notice that as a function of x, this is a low degree polynomial. We are multiplying at most k, or exactly k, of the variables. So each monomial is of degree k exactly. In fact, we can read off the coefficient from this equation. All the coefficients are of the same magnitude. And it's a quick calculation to see that the sum of absolute values of coefficient of degree k is exactly square root n to the k minus 1. This is rather large. There are at most n choose k such coefficients, and the sum of absolute values is roughly square root of this size. On the other hand, if we take any randomized decision tree that makes d queries, or in other words, is of depth d, and we look at its acceptance probability, then the L1k, or the sum of absolute values of coefficients of degree k of this polynomial, is at most square root d to the k. So you can see that if we are making constant many queries, this behaves like some constant to the k, whereas in the case of the quantum algorithm, it behaves like square root n to the k minus 1, something that depends on n rather than something constant. Unfortunately, this is not enough to deduce the result. It could be that two polynomials are very similar on all possible Boolean inputs, but have very different sparsity the way we defined it. So what we really want, we want some distribution over inputs that demonstrate this difference of sparsity. In other words, we want some distribution that the only way that you can solve the problem on this distribution is if you are a dense polynomial. This is what we establish. We come up with some hard distribution for this k-fold Rorrelation problem. We define that distribution DMK and show that the following holds. On one hand, if you sample according to the uniform distribution, then with high probability, you would get a no instance. You would get k vectors whose Rorrelation is rather small. On the other hand, if you sample according to DMK, you get, with constant probability, a yes instance. And the third bullet, which is the hardest one, is to show that a shallow decision tree cannot tell the difference between these two cases. Combining these three items together, you can show that this distribution that samples with probability 1/2 an input from DMK and with probability 1/2 an input according to UK is a hard distribution. It's hard for shallow decision trees to solve inputs sampled from this hard distribution. Okay. So I want to mention briefly how this distribution looks like. Okay, so we start with the distribution defined by Aaronson-Ambainis DM2. So this is for the case of k equals 2, or rather the case where we need to output 2 vectors. We start in the Gaussian world. We sample y to be a multivariate Gaussian with n coordinates. Each of them is a standard Gaussian, and all these coordinates are independent. Then it takes this n-dimensional vector y, multiplied by the matrix M, and get an n-dimensional vector z. We take these 2 vectors, and we transform them into Boolean vectors by taking the sign of every coordinate. This distribution generates pairs that are with high probability, twofold Forrelation. This was shown by Aaronson-Ambainis. This distribution can be distinguished from the uniform distribution by a constant query algorithm. In fact, the query algorithm that we already have seen. And on the other hand, Aaronson-Ambainis showed that a randomized algorithm must query at least square root n coordinates to distinguish this distribution from the uniform. But this is tight. They also showed that there is a randomized algorithm that can tell the difference, that makes at most constant times square root n queries. How can we improve this? The idea is as follows. We're going to sample 2 correlated pairs. Y1, Z1 is one copy of a correlated pair, where a correlated pair is exactly the distribution defined in the previous slide. Y2 and Z2 are a completely independent new correlated pair. And now we are taking 3 vectors. X1 will be Z1, X2 will be Y1 pointwise product with Z2, and X3 would be Y2. So this lives in the real world, and if we want to take it back to the Boolean world, we need to take signs of every coordinate. The intuition behind this choice is as follows. If we just pick 2 uncorrelated correlated pairs, and we just put them one next to the other, and we want to say, can we distinguish this from the uniform distribution, then an algorithm can just ignore the red vectors and just look at the green vectors and apply the query algorithm that distinguish these green vectors from uniform vectors. The idea is to hide this correlation between Z1 and Y1. How can we hide this? We can hide it by multiplying Y1 and Z2. The quantum query algorithm that can distinguish Y1 and Z1 from the uniform 2 vectors relies on many pairwise correlation between these vectors. However, when we multiply Y1 by Z2, these pairwise correlations disappear, and we are only left with freewise correlation or correlations that involve more than 3 coordinates. And in fact, these freewise correlations are much weaker than the pairwise correlation. This is very high-level intuition, and the argument itself is a little bit more complicated than that. Because in particular, we need to worry about correlations that come from all possible moments, not only the third degree moments. This brings us to the main result, showing that DMK is pseudorandom against deterministic and randomized decision trees. The statement of the result is as follows. If f is a decision tree of depth n to the 2/3 minus O of 1 over k, then the acceptance probability of f under the uniform distribution is very similar to its acceptance probability under DMK. The difference between the two is little O of 1. Recall that f of x can be written as a multilinear polynomial. This polynomial captures the acceptance probability of the decision tree on input x. We have a coefficient for each subset, as, and we have a monomial, x to the s. To bound the difference between the acceptance probability, it suffices to bound the contribution to the difference of each individual monomial. This can be carried out by a simple linearity of expectation and triangle inequality. you can show that the difference of acceptance probability is at most the sum over all sets, the absolute value of the coefficient, multiplied by the difference of the expectation of the monomial on U and on DMK. You can further simplify, since the expectation under the uniform distribution is 0 for all monomial except for the empty monomial. And this brings us to the third line, which can be achieved by just gathering all sets according to their degree. So we show that this is at most the sum of absolute values of a certain degree multiplied by the maximal absolute value of a monomial of this degree. So to finish the proof, you need to show that this L1L is not too large and that these moments or the expectation of these monomials are rather small. Both of them are technically involved and they take most of the technical part of the paper. I want to mention that although we get bounds on the sparsity of deterministic decision trees and randomized decision trees, we believe that better bounds are correct. We conjecture that the bounds could be improved to square root d choose L, whereas the bound that we get are square root d to the L. So they are sort of square root L factorial better than what we achieve. Notice that this is not a big difference for small values of L, but it is a big difference when L grows. In fact, if this conjecture is true, then the lower bounds that we get to the randomized query complexity of Rorrelation can be improved to n to the 1 minus 1 over k. This gives optimal separation between the quantum query complexity and the randomized query complexity if the conjecture would be true. Let me mention one consequence of this result. Via this cheat sheet technique that I mentioned earlier, we can get actually a total Boolean function that is defined on all possible strings of length n, where the randomized query complexity is at least a quantum query complexity to the power 2 plus 2/3, minus little o1 factors. And if you assume the conjecture, this grows to a nearly cubic separation. Finally, I want to finish with some exciting news. Quite recently, this conjecture about the L1L of shallow decision trees was proved by Sherstov, Storozhenko, and Wu. They were able to prove the conjecture as it was stated in these previous slides. And based on that, you can show that the Rorrelation is a problem that gets constant quantum query complexity, and on the other hand requires n to the 1 minus 1 over k randomized query complexity. This gives the optimal separation between quantum and randomized query complexity. This result was also obtained by Bansal and Sinha, and moreover, they made this separation explicit, meaning that their result works not only for a random matrix M, but for the Hadamard matrix. The result is based on tools from stochastic calculus. This has been a challenging approach that I tried and failed. The third question is, what is the best quantum speedup for total Boolean functions? Based on these results, in bullets 1 and 2, we know that there are cubic separations between the two. Based on recent results, we know that the separation can be at most quartic. But what is the real exponent? Is it 3, 4, maybe something in the middle? So I'd like to end with that, and thank you for joining me.